What is a scalar quantity? A scalar quantity is a quantity that has got only magnitude. So that means we can describe such a quantity with the help of a simple number. Some of the examples of scalar quantity includes mass. For instance, we can denote the mass of an object as 2 kg or 30 grams, etc. Then we can also consider length, simple length measurement as a scalar quantity. For instance, we could consider the length of a rectangle to be of, let's say, of 2 centimeter. Then we can also have temperature. Temperature is a best example of a scalar quantity. Because, for instance, if we say that the temperature of a particular object is at 30 degrees Celsius, that simply means that it is just a number. So it does not depend on which location we measure. It's always going to be 30 degree. It means independent of location. Then we could have the volume of an object, the volume of a box, for instance. So the volume of a box is just a simple scalar number. For, let's say, this volume is 20 cubic centimeter. Yeah, that's a fixed number, as a simple number. We could have, since we are talking about electromagnetism, so electric potential, so this is going to be a quantity that we'll encounter later on. This electric potential is a scalar quantity as well. That means it's not dependent on direction. We can simply quantify it with the help of a number. Then we could have energy. We can also consider an example of an energy of an object or energy of a system. These are all scalar quantities. Now, on contrary to a scalar quantities, we could have a vector quantity. A vector quantity is something which has got both magnitude and direction. The best example we can think of right now is a force. Force applied on an object. Let's say we have a object, so an object of some mass m. So that means it is a scalar object. Now, if we apply some force on it, let's say we are applying the force from the left hand side to the right hand side, it is evident that this particular object is going to move in the right direction. If we change the direction of the force, let's say we change the direction of the force in this particular fashion, then our object is going to move along the line of the force. So that means it definitely has a direction. Of course, more the force, the more will be its displacement. Lesser the force, less will be the displacement. So a force is a quantity that depends both on the magnitude as well as the direction. Then we could have velocity. Velocity is a vector quantity because it has got magnitude and it has got a direction as well. And one example is speed. Let's say we consider speed. Speed is a scalar quantity because when we say that the speed of an object that's 2 meters per second, that means it's moving with a speed of 2 meters every 1 second. But if we want to make it into a velocity, that's when we attach some direction to it. Let's say the speed of an object is 2 meters per second moving in some particular direction, moving north. So in this case, then the speed of the object along with the direction is going to be referred to as the velocity of the object. Okay. Then we could have displacement. Now displacement is the movement of the object from one location to another. So that is a vector quantity because it depends on direction. So let's say we have 3 points A, B and C. Now the displacement of an object going from A to B is very different from the displacement of the object going from A to C. It is direction dependent. So that means displacement is going to be a vector quantity. And in terms of electromagnetism, we have a quantity referred to as the electric field or electric intensity. Let's call it electric field for the time being. The electric field, as we will see later on, that this is going to be a vector quantity. So it has got a direction. Okay. So now that we have identified what scalars and vectors are and what differentiate them, the main differentiation is that vector quantity has got direction as well as magnitude, whereas scalar has got only magnitude. Now, it is very important that we can distinguish between vector quantities from scalars quantity. So, let's say we take a vector quantity A. Now, if we simply use the letter A, then it means that this is a scalar quantity. So, a scalar quantity. Now, it's not necessary that we use only uppercase later. We can use lowercase letters as well, but these means that this is a scalar quantity. But if we want to show that these are not scalar but vector quantities, all we have to do is use the letters, and then on top of these letters we are going to use an arrow sign, arrow going from left to right. Similarly, for the uppercase letter A, we're going to place an arrow over top, and that represents a vector quantity. So these are vector quantities. Now, in textbook, there are different ways of writing. Generally, in textbook, vectors are usually represented by bold case letters. However, for our case, we will be mostly using some letters, and on top of it, we are going to use the arrow sign. Right. So that means graphically, we can represent, if we consider a vector, graphically, it simply means that a vector which is represented by a straight line, this length is going to represent its magnitude. And if we show that this is going in some particular direction, we show an arrow, and the arrow is the direction of the arrow is going to give us the direction of the vector quantity. Now, as I've mentioned, that a vector along with direction, it's also going to have a magnitude. Then how do we show that this particular a vector is going to have some magnitude? So what we'll do, we're going to place the vector inside two vertical lines, and that's going to represent the magnitude. So we'll say that this is the magnitude of the vector quantity A, vector A, or simply A vector. Right, that is how we can represent the magnitude of a vector. So if you use lowercase letter, we'll put an arrow on top of it to represent it as a vector with having some direction. And if we only want to talk about its magnitude, then we are going to place it inside two vertical lines, also referred to as the modulus in math. So let's try to grasp the idea of vectors with the help of direction. So here we have the axis, we have the x-axis and the y-axis. So on the y-axis we have the north and the south direction, and on the x-axis we have the east and the west direction. So how do we represent vectors? So if we show a vector pointing upwards, this simply means that this particular vector is pointing in the northern direction. Then we could have a vector B pointing in the east direction. We could have a vector which could be pointing in the northeast direction. That means this particular vector is making an angle 45 degree with the north and also 45 degree with the east. So this is going to be the vector C along the northeast direction. Then we could have a vector pointing along the southwest direction, meaning it is going to make an angle of 45 degree with each south and west direction. Fine. Now the question comes, when can vectors be equal? So we'll talk about equality of vectors. Now there are two conditions that must be met in order for two vectors to be equal. So that means if we say that if we have two vectors A and B, if A vector equals to B vector, this must mean that magnitude of the two vectors are exactly equal. That means the magnitude of vector A equals the magnitude of vector B, and both are along or pointing in the same direction. That is the criteria. It must be in the same direction. For instance, we can say, so let's say this is a vector A which is along the northeast direction, and we have another B which is also pointing in the northeast direction. And if the magnitude, which is will be simply in the diagram form, we can say that the length of the arrow of A is equals to the length of the arrow of B, then we can say that the two vectors are going to be equal to each other. So that's what we mean by equality of vectors. If these two criterions are not met at the same time, we cannot say that the two vectors are equal. Even if, for instance, another example is, let's say we have a vector A which is pointing in the northeast direction, and we have another vector B which is pointing in the southwest direction. Now for this particular two vectors, here the magnitude of vector A equals the magnitude of vector B, suppose. But the directions are completely different. They are in the diametrically opposite direction. So in the for this particular scenario, we cannot say that the two vectors are equal. So here A vector will be unequal to the vector B, even though they have the same magnitude. Just because their direction does not match, we cannot say that the two vectors are equal to each other. So these is a very important criterion, that the magnitude as well as the direction of the vectors must be same. Only then we can say that the vectors are equal to each other. Okay, now we have talked about equality of vectors. Moving on, now we'll be understanding how to add vectors. How to add vectors. Once we understand addition, then we'll come to the subtraction part. But first, let's try to understand how to add two vectors. We're going to start with two vectors. Let's say we have a vector A and we have a vector B. Both are in different direction. Now to add vectors, we have to understand two terminologies. This is the starting point of the vector. The starting point of a vector is referred to as the initial point. Initial point of the given vector. That's the initial point. And where we have the arrow, the end of the arrow point. So this point is going to be referred to as the terminal point. Now that's the end of the vector. So every vector has got these 2 points, the starting point and the end point. The starting point is the initial point and we have the terminal point. So what we'll do, in order to add two vectors, we are going to use the concept of displacement here. Concept of displacement states that we are going to move this vector around this writing pad. So we are going to move, and when we move, we have to be very careful about this. We cannot alter the properties of this particular vector. Meaning, let's say we're going to pick up vector A and we're going to place, let's say, in this particular position. We're not altering its property means that we are not going to vary the length of the vector A. If its initial length, let's say, was 2 centimeter, so when you move it anywhere along this particular writing pad, we are not going to alter its length. So it's going to stay as 2 centimeter. And also, its direction must not be altered at all. So whatever was the original direction of vector A, it should be there. So here what we're doing is actually we are taking another vector A which is equal to the original vector A. In fact, they are clone of each other. Now what we do? Now we'll have the initial point IP and then we have the terminal point TP. Now what we'll do? Now what we're going to do? We're going to pick up the vector B. Now we are also going to move this vector B without altering any of its properties. That means we are going to keep its length and its direction intact. And we are going to go inside the initial point of vector B with the terminal point of vector A. So let's place it. So this is going to be the vector B. So making sure that the length and the direction of vector B is not altered at all. So here all we have to do is go inside the initial point of vector B with the terminal point of vector A. Now to add the two vectors, all we have to do is join the initial point of vector A with the terminal point of vector B. So when we join this, we're going to get a third vector. So this third vector is going to be referred to as the sum of the vector A and B. So A vector when added to B vector does give rise to a new vector, and we're going to name this vector as the vector C. And the way to do it is all we have to do is join the terminal point of one of the vector with the initial point of the other vector. So we could have here, so in this particular example, we started with the vector A and then we added vector B to it. I'm going to show you that the vector addition, so this is vector addition. Vector addition is commutative in nature. That means we can change the order and still we're going to get the same result. So what we'll do this time, we're going to start with vector B. We're going to displace this vector B and bring it to a new position. This is our vector B. So where the terminal point of vector B lies, from here, we're going to join the initial point of vector A. Now we're going to pick vector A and we're going to place its initial point with the terminal point of vector B. So this is going to be vector B A. Now what we do to find out the sum of the two vectors, we're going to start from the initial point of vector B and then join the terminal point of vector A, and that's going to give us the vector C. Now as we can see here, this particular vector C is parallel to the vector C that we obtained when we added A to and then B later on. Now that means this particular triangle law of addition tells us we take vector B first and then add vector A to it. This is also going to give us the same vector C, whose magnitude and direction is going to be same as the vector C obtained when we first took vector A and added B to it. So that means this will be equals to the vector A added to vector B. So that's a property of vectors. So here vector addition, so we can write that our vector addition is going to be commutative in nature. Vector addition is commutative. Okay. Now, vector addition also follows the law of associativity. So law of associativity, if you recall from numbers, let's say we have three numbers A, B, and C. We're going to add them. So what we do, we can add only two numbers at a time. So that means we can first begin by adding A and B first, and whatever result we get, we can add it to the third number C, and this result is going to be exactly the same as adding B and C first, and whatever result we get, we're going to add it to A. So this is called the law of associativity. So this holds true for vectors as well. So let's try to understand vector addition by taking three vectors, and we're going to verify that the law of associativity holds true for vector addition as well. Let's say we take three vectors. We have vector A, vector B, and vector C. Now each of the three vectors have different magnitudes, and all three of them are pointing in different direction. Now what we do, we want to add the three vectors. Let's first check out by adding vector A with vector B together, and once we get the result, we will add it to the third vector C. Now all we have to do is we'll take vector A, and then we're going to displace it to a new location. So that's it. This is the new location of the vector A. As you can see, I have not altered the length of the vector A, that means the magnitude of vector A, as well as direction. So this is going to be our vector A. Now we have the terminal point of vector A. Wherever the terminal point of vector A is, we will be coinciding with the initial point of vector B. Okay, so let's pick up a vector B. Let's copy this particular vector, and then we're going to paste it over here, and we'll try to coincide this vector with the initial point of vector B with the terminal point of vector A. Right, so we coincided. Now after this, what we'll do, we're going to take, so this is done. So let's find out the sum of vector A and vector B. All we have to do is join the point from vector A, from the initial point of vector A and the co-terminal point of vector B. So we take from vector A and join the co-terminal point of vector B. So this is going to give us a new vector. Let's call it vector. This is not vector C, this is vector D. So we have the sum of A and B that is giving us a new vector, which is the vector D. Now what we'll do, we are going to add vector D with vector C. So that means we are going to take vector D. Or let's keep it in this fashion only. Now what we'll do, we'll take the vector C and we will coincide its initial point with the terminal point of vector D. Okay, so let's copy vector C so that we do not alter its direction and magnitude. Now we are going to join vector C and vector D. So here we have vector C, the initial point of vector C joined with the terminal point of vector D. So we only have to look at vector D and vector C. We don't have to look at vector A and B anymore because we already found its sum, which came out to be the vector D. So we'll start from vector D and we're going to join this with the co-terminal point of vector C. So this is going to be the vector D added with C. So this particular vector is vector D added to vector C. And D, as we have already mentioned, that's A plus B. So what we have done here is A plus B. We have added it first, and to it we have added the vector C. Okay, now what we'll do next, we are going to add vector B and vector C first. And whatever result we get, we are going to add it to vector A. So let's call vector B plus C to be the vector E. So again, what we'll do, we'll now this time pick vector B first. We'll start with vector B. Let's do it over here. We have vector B. Let's name it so that we don't get confused. This is our vector B. Then we're going to consider vector C. Let's copy vector C and then we're going to paste vector C. Vector C should be pasted in such a way such that the terminal point of vector B coincides with the initial point of vector C. Fine. So we have added V and C. Now to find out the sum or the resultant, which is referred to as generally, we will start from the initial point of point B and joined the from here we are going to start a vector and we are going to join it with the terminal point of vector C. Starting from B, we're going to go to the terminal point of vector C. Right. So we're going to call this the vector E. So now we will take vector E and we are going to, okay, so what we have to show here is we have to take A vector first and then add it with B plus C. So what we'll do, since it is commutative, it doesn't matter. So we can take E vector and then add it to vector A. We should get the same result. We have already established the fact that vector addition is commutative. Now let's take vector A. So we're going to copy vector A and then we're going to place vector the initial point of vector A and coincide it with the terminal point of vector E. So now we have the vector E. We need to add vector E with vector A. So here what we'll do, we'll go to the initial point of vector, that is initial point of vector A, this is the point, and then we have the terminal point of vector A. We need to join these two with the help of a vector. So we'll start from the initial point of vector E and join and move it to and extend it to the terminal point of vector A. So we're saying that this is the vector which is the sum E vector plus A vector. Let's verify that the vector that we obtain by adding D and C is equals to the vector E plus A. So all we have to do is we're going to take this the earlier vector, copy it and paste it over here. Okay, right? So this is the vector. We're going to name this as the vector A plus B, which was obtained by first stating A plus B, and then to it we added the vector C. And then we're going to consider the vector that we obtained just now. So here we have the vector. Let's keep it side by side, which will be easier for us to compare. So this is the vector which was obtained by adding vector A to the sum of the vector B and C. Now, by eyeballing these two arrows, we can say that they have the same length and also they have the same direction. So here we have verified that the vector addition also follows the law of associativity, meaning we can take vector A, add it to the sum of the vectors B and C. The result is going to be exactly the same as taking the sum of vector A and B first and then we add the vector C to it. Or we can do the other way around. We can take vector A and add it to vector C and then whatever result we get, we add it to the second vector, that means B vector, and we're still going to get the same result. So we have established the facts that vector addition is also associative in nature. Now that we have understood how to add vectors, the next task will be to understand how to subtract vectors. Now before going to subtraction of vectors, we need to understand the scalar multiplication with a vector, scalar multiplication of some scalar quantity with a given vector. It's a very simple idea. Let's say we have a vector with some magnitude A. Now, what we do is we multiply the vector A with some number. This 2 is a scalar number. This is a scalar number or scalar quantity, we can say. Now, on multiplying the vector A with the scalar number, what we'll see here that the vector, it's going to retain its direction. Earlier it was direction in the fashion as is shown here. It's going to retain its direction, but what we will see here that the magnitude of the vector has doubled. So that is the meaning when we say that we have multiplied a vector with a scalar number. If we multiply that same vector with a scalar number 3, then what we'll see that the vector is going to get increased by a factor of 3. That means it will get tripled, but the direction is going to remain the same as the original vector. Okay, now that we have understood how to multiply a vector with a scalar number, let's do one thing. We'll take the same vector A, but we are going to multiply it with some scalar number which is -1. So -1 times A vector, that's simply -A vector. This means that we'll take the vector A. This time we're not going to change its magnitude, but we are going to change its direction. So this is going to be -A vector. Now that means whenever we multiply a vector with a negative number, its direction changes. It becomes exactly opposite to what it was earlier. Now, what we can do, let's say we take vector A and then we multiply it with the scalar -2. So we have -2 multiplied to A vector, which is simply -2A vector. Now, an interesting thing is happening. We take the vector A, we are going to double this vector. So the magnitude of the vector has doubled, and also because of this negative sign, whatever direction it was having initially, that will become the opposite of it. So we have the new vector -2A. It is exactly in the opposite direction to that of the vector A, and also the magnitude has doubled. Okay, we can also take negative half of the vector A. So all we have to do, initially if it was having some magnitude of, let's say, 2 centimeter, now it will become 1 centimeter. It has become half of the original value, and the direction has also changed. So this is the vector -half A vector. I think it's pretty much clear how we can add scalar numbers with a vector. Now that we understand the meaning of how to make a vector negative, we can now go for vector subtraction. So here we have two vectors, vector A and vector B. Our goal is to subtract vector B from vector A. So that means we have to find A vector minus B vector. Okay, let's try to understand it. So what we'll do, we can rewrite A vector minus B vector as A vector added to negative of B vector. So what we're doing here, we're just rewriting the vector negative B vector as a vector. Oh, okay, let's further simplify it. We can rewrite it as A vector added to -1 multiplied to V vector. Now that becomes easier to understand. All we have to do is take vector B and then multiply it with a scalar which is -1. This means that we will get the same vector B, means the vector having the same magnitude as vector B, but its direction is going to be opposite to that of the original vector. So we're going to consider a vector B whose direction is opposite to that of the original vector. So that's why we're multiplying it with -1. Now, -1 suggests that it is in the opposite direction to that of the original vector. Now what we'll do, we can call this another vector, C vector only, where C vector is nothing but -B vector. So now our task is to add vector A with vector C. Now that's a simple vector addition. So what we have done, we have converted our subtraction to an addition. Now we can easily add the two vectors. All we have to do is you can start by picking either vector A or vector C. So let's pick a vector A. So we have here vector A, we have vector A. So wherever the terminal point of vector A lies, there will be coinciding the initial point of vector C or the -B vector. Okay, so let's pick up -B vector. We have -B vector, but we're going to be very careful here. We'll be carefully placing the initial point. Now we have -B vector, which we are naming it as C vector for easy to understand purpose. Now we have to find the sum of the two vectors, A vector and C vector. All we have to do is start a vector from the initial point of vector A and move the vector move the vector in such a fashion such that its terminal point coincides with the terminal point of vector C or vector -B vector. So here we have the vector starting from the initial point of A vector and terminating at the terminal point of -B vector. So this is going to be A vector minus B vector. Okay, so we have successfully understood how we can add vectors and subtract vectors. To give you a gist of why we are going through the pain of adding and subtracting vectors, because if we want to think in terms of addition of forces, so let's say we have some particle here and this particle is acted upon by different kinds of forces. So we have force F1 acting on it, so force is a vector quantity. Then we have another force F2 acting on it. Then we have another F3 force which is pulling this particle in its direction. So the question is like, what will be the resultant of the force? That means what will be the final direction of this point? The point has to move in some particular direction. So that is going to depend on the magnitude and the direction of all the three forces, where the sum of the vectors becomes extremely important. We'll deal with this problem later, but I wanted to give you a graphical understanding of why we need to add and subtract vectors. Next, we will be discussing an extremely important concept that is referred to as unit vectors. What's the need of unit vectors? Let's think about it in this particular fashion. Let's say we have a scalar quantity A. Is there any way we can convert this scalar into a vector quantity? Is it possible? In other words, if we want to think in terms of a physical example, let's say we have a ball that has some kind of a mass. Let's say it has a mass of 20 gram and it is stationary. It is just sitting somewhere. Now the question is there any way we can convert this problem into a vector problem? All we have to do is pick up this particular ball and fling it into the air. So let's say we throw it upwards, then what will happen? It is going to move in a parabolic position. And the parabolic position tells us that at different points, it's going to have different direction. Now that is the reason why, and that is how we have successfully converted a given problem into a vector problem. So that means it is indeed possible to take a scalar quantity and convert it into a vector. So this is where the concept of unit vectors comes into play. The concept of unit vector is such that, let's say we're going to call this 1. A unit vector, as the name suggests, it has something to do with unity or 1. So let's say we have a vector 1. The representation wise, what we'll do, we're going to put some cap on top of it to tell us that this is a very special type of vector. This is not a normal vector that we usually talked about by putting an arrow on top of it. Here we are putting a cap on top of it. Now let's say this is a very special type of vector. So when we take this vector and multiply it to the scalar number, this particular scalar number, it does not alter the magnitude of the scalar number. That means this number initially it had a magnitude of A, so it's going to have the same magnitude even after multiplication, because we know 1 is an identity. Whenever we multiply it with 1, the property of the number remains intact. Let's say if we take the number 2 and multiply it with 1, we get 2 only. So that means the magnitude of the number 2 has remained unchanged. So 1, that's why we call 1 as an identity. Now akin to this idea, we can say here that we take a scalar quantity, multiply with this very special vector, which is referred to as the unit vector. We get something whose magnitude is same as the original one. Its magnitude is the same, but we now have a special thing happening with it. That means now the direction of this vector, this unit vector, has been given to the scalar quantity. That means now what we have is a vector. Right? And this vector is going to have a magnitude same as that of the original scalar number, and it's going to have a direction since it's a vector, and its direction is going to be same as that of the unit vector. So the definition of a unit vector is that if we take a scalar and multiply it with some unit vector, so the best way to represent a unit vector is take any scalar number and put a cap on top of it. Then this particular scalar number is going to now become a vector with an arrow, or it's going to become a with a arrow on top of it, suggesting that it is a vector whose magnitude, the magnitude of this particular vector, is the same as that of the original scalar number. And the direction and it's this direction. It means its direction is going to be, its direction will be the same as that of the unit vector. It's same as that of the unit vector. So I think you have gotten some sense of what a unit vector is, right? So what we'll do, we'll take this particular equation. So we have a vector, we are multiplying it with a very special vector known as the unit vector, and that converts the scalar number into a vector. What we can do, we can keep a cap on the left hand side and divide throughout with a scalar number. We can do division by scalar number. That means we have a vector over a, which also tells me that means if we have a vector, a vector equals to b vector, we cannot actually divide vectors. That's not allowed in vectors. That means if we write, let's say for some vector c, if we do this particular operation is not allowed in a vector. We cannot do division in vectors. Okay, but what we can do, we can take this vector a vector equals to b vector, we can divide it by some number. So let's say 3 is a scalar number, we can divide both sides with 3. So here what we have done, since a is a scalar number, we have divided both sides of this equation with a scalar number, so that gets rid of the vector a on the left hand side. Now we have the definition of a unit vector. So that means Take a vector, take any vector, let's say take any vector, and divide this vector with the magnitude of that vector, which is represented in this particular fashion. Then what is left behind is only the direction, because we are dividing the magnitude, dividing the vector with its own magnitude. It only leaves us with the direction of that particular vector, and that vector is referred to as the unit vector. That means every vector has its own direction, and that unique direction can be obtained by using the definition of the unit vector. So let's say if I have a vector A vector, to define its direction, all we have to do is take that same vector A, find its magnitude, that means the length of the arrow, divide the direction with that magnitude of that vector, and whatever we get, whatever result that we get, that is going to be a unit vector. That is the direction of the vector. So that means by definition, the magnitude of the unit vector is always going to be 1. And if we take another vector B, this B vector, to find its direction, which we refer to as the unit vector, all we have to do is take its vector, take the vector, divide it by the magnitude, we get the unit vector. And here A cap and B cap we refer to as A cap, that's how we call it, and this is going to be called B cap. So here A cap and B cap, these two vectors are not equal. For this particular example, they are not equal because they have completely different direction. Now thus a unit vector is an extremely powerful idea, and we will understand its importance once we understand how to resolve a vector. That will come in sometime later. So let's now talk about how to multiply vectors. We have talked about how to add vectors. We talked about how to subtract vectors as well. Now the question is, how do we multiply two vectors? The multiplication of two vectors. All we talked about when we were discussing multiplication, we only talked about how we multiply a scalar with a vector. So that's allowed. We take a scalar number and we can multiply with some vector A. So it only increases the magnitude of that vector. It does not changes the direction of that particular vector. However, in the case when we are multiplying with a negative scalar number, in that case the magnitude of the vector is going to get scaled by that vector, and also its direction is going to be opposite to that of the initial direction. But this time we're talking about a completely different idea. What we're discussing is the multiplication. That means we have a vector A. What is the product of this particular vector with another B? Unlike in the case of numbers, let's say we have two numbers 2 and 3. We can find the product of the two numbers. That's simply 2 times 3 will be equals to 6. But in case of our vector multiplication, we do not use the usual route that we take while multiplying scalar numbers. Here we have to be very careful. There are two kinds of multiplication that are allowed in a vector. So let's talk about it. One is going to be referred to as the dot product. One is going to be referred to as the dot product, and the other one is referred to as the cross product. So we have a dot product and we have a cross product. Now let's try to understand how to first represent a dot product and a cross product. So that means we are going to multiply two vectors A and V. If we want to take the dot product, it's not a regular product. It could be either a dot product or a cross product. So dot product means we just put a dot between A and B. Now putting a dot in between A and B suggests that we are taking a dot product, and some textbooks also write it as vector A. So we put a dot inside a circle to represent it as a dot product between A and B. However, for our general purpose, we'll be using simply a dot between the vector A and B, telling us that we are working with a dot product. Now for cross product, as the name suggests, we're going to put a cross between two vectors A and B. This is not the regular cross that we use when we are multiplying numbers. This is a special type of cross. So that's why some authors, in order to distinguish that this is not the cross that we are talking when we multiply two numbers, so they put a cross inside a circle, telling us that this is a cross product. This is the multiplication of two vectors. Now the question is, why do we need two different types of product whenever we're multiplying two vectors? We could multiply multiple vectors as well, but let's start by multiplying two vectors at a time. The reason why we are classifying products and vectors in two categories as dot product and cross product, because each of them has a unique property. So Of course, whenever we take the product of two numbers, it's going to give us a single value, right? So if we multiply 3 with 5, that's going to give us a unique single value, which is 15. Similarly, when we multiply two vectors, it must give us some kind of a quantity. Now, when we take the dot product, it always gives us a scalar quantity. So this is going to give us a scalar quantity. That's a definition of a dot product. So dot product is also sometimes referred to as the scalar product. Now, whenever we take the dot product between two vectors, the result is going to be a scalar number. And in case of a cross product, the result of these two vectors is going to be a vector quantity. So that is what distinguishes a dot product from a vector product. So let us first begin by understanding how dot product works. So to understand the dot product of two vectors, we begin by considering two vectors. We will be considering vector A and we will be considering vector B. Okay. Now it's very important how to work with dot products. So first we will take vector A and then we're going to combine vector B with A in such a way such that both of the initial point coincide. So let's say this is our vector B. As we can see here, the initial point of both the vector A as well as that of vector B coincide. And we can see here that both of them is going to make an angle theta with them. Right? Now, let me try to draw it properly. So as you can observe here, the vector A and vector B are inclined to each other with an angle of theta. So here the initial points are coinciding. Now, to understand what is a dot product, it actually has to do with the projection of one vector onto the other. That means here, let's begin by first trying to understand what is the meaning of A vector dot B vector. It has to do with how much of vector A is projected along B. That's the meaning of a dot product. So finding the projection, think of it in this particular fashion. So let's say, so this B represents a vector which is lying on a floor. So let's say this is the floor and we have a stick which is represented by the vector A. So it has got a magnitude and is also pointing in some direction. Now, from the upright position, let's say we are going to shine a light on top of the stick, which is the vector A. The vector A or the stick is going to cast a shadow on the floor. So this is going to be the projection. This length, let's call it some C. Some scalar number C. So this is going to be, let's call it C, is going to be the projection of A vector on B vector. This particular length is the projection of vector A on C, and also it's dependent on the angle theta. Smaller the angle theta, it's more towards 0, then more will be the projection of vector A along B, and more the theta is towards 90 degree, the lesser will be the projection. Okay, now in this, so here we'll be using a little bit of trigonometry here. So clearly we can find out the value of C. Now if we use the concept of a right angle triangle, so here we can say, let's name it as PQR. So here we have a right angle triangle. In the right angle triangle PQR, let's try to define cosine of the angle theta. The cosine of the angle theta, that's defined as the adjacent, which is QR, divided by the hypotenuse, which is QP. Now what is QR? So QR, that's nothing but the projection of vector A on C divided by QP. QP is going to be the magnitude of vector A, right? We're not going to consider the direction, only the magnitude. So if we rearrange the terms, we're going to get C equals to the magnitude of vector A times cosine of angle theta. So here we can see say that C is going to be the projection of, or the length of the shadow of vector A along B. But we also want to understand how much of the projection is along the vector B. To find out how much is the projection of C along B, this is what is referred to as the dot product between vector A and B. To find out how much is the projection, how much is the shadow along B, we'll have to take this projection scalar quantity C and multiply with the scaling factor, which is the magnitude of the vector B. So this amount is going to tell us the total amount of the projection of vector A, or we can say the total amount of shadow that is present along the vector B. Now if we replace the value of C with absolute value of A, or the magnitude of A times cosine theta, so we get absolute value of A times cosine theta times absolute value of B Okay, absolute value is also going to be referred to as the magnitude of a vector. In some lectures are going to be referred to as the magnitude of the vector A, or sometimes I refer to it as the absolute value. They'll mean the same thing in this particular context. Now that means we have obtained that A vector dotted with B vector, so this is going to be equals to the magnitude of vector A times the magnitude of vector B times cosine of the angle between them, and this is the definition of the dot product of two vectors. So that tells us how much one vector is projecting along B vector. Now here, vector dot product is commutative. That means A vector dot B vector is the same as V vector dot A vector. All you have to do is shine a line on vector B. So here we can see the vector B is going to cast some kind of shadow on the vector A. So here also we can see how much of the projection of B is along A, and we multiply it with the magnitude of A to get the full picture. So that is referred to as B vector dot A vector. So this is how we can find out the product of two vectors, and this is a special type of product referred to as the dot product. Now also mathematically we can see here that once we take the magnitude, then magnitude of A vector, this is going to be a scalar number. Similarly, magnitude of vector B, that's also going to be a scalar number. Cosine of theta, that's going to be a scalar by definition. So we have three scalar numbers getting multiplied to each other, and definitely it is going to give us a scalar value or a scalar quantity. And this is the reason why we say that the product of two vectors, if we take the dot product of two vectors, the resultant is always going to be a scalar quantity or a scalar number. Now let's go to the other kind of product, which is the cross product. Now that's a very special type of product. So let's try to understand the vector product, or also commonly referred to as the cross product of two vectors, the cross product. Now it's going to take some understanding to or it will need some kind of practice to get familiar with the concept of a cross product. Let me try to explain this to you. Let's say we consider a table. On top of this table, on this plain table, we're going to consider two vectors. Like in the previous case, we're going to consider the vector A and another vector B. And also this time here, the two vectors are the initial point of the two vectors are coinciding, such that it makes an angle of theta with each other. So here we have a vector A with vector B. Now, it's very important. Earlier in the previous case, we say that the vector dot product is commutative. But here, if we take a vector A, cross it with vector B, then this is never going to be equals to taking the vector B first and then crossing with vector A. This will become evident in a moment why this is not true. Now, to understand A vector cross B vector, so think of it like this. Consider your right hand. Now, consider your right hand. Now we are going to curl our fingers, our four fingers, going from A towards B. We're going to curl our fingers representing the direction that we're going from A cross B. That's the meaning of A cross B. We're going from vector A towards vector B. Then our thumb is going to point upward. So this is going to be the direction of the thumb, which is going to be perpendicular to the tabletop. So this is going to be a new vector C. So here I'm saying that if I take a vector A, cross it with another vector B, that this is going to give us a new vector C, with the condition that this C vector is going to be perpendicular to both A vector as well as B vector. That's the condition of a cross product. So taking the cross product between two vectors yields a new vector, and that vector is going to be perpendicular to the plane containing the vector A and B. Now, let's understand why B vector cross A vector is not equals to A cross B. Now what we're doing here, now this time we're coming from B vector to A vector. Now once we come from B vector to A vector, in a clockwise fashion, we have to be very careful. This time our fingers are going to, the four fingers are going to start from B and curl towards A, and we will see that our thumb is going to point downwards. So that means we're going to get negative C vector. Is going to be exactly opposite to that of C vector. So this is going to give us a negative C vector, telling us that that's why that A vector cross B vector is never equals to B cross A. So here I'm saying that B vector cross A vector is giving me the same vector C, but this time it's in opposite direction. So that means if we combine this idea and this idea, we can say that A cross B, that's not commutative in nature, But A vector crossed with B vector is going to give us negative B vector cross A vector. So that's the meaning of a cross product. Now I will not go into the derivation of how to find out the vector cross product. I'll straight away give you the idea. That means if we have a vector A, we are crossing with another vector B. The order is extremely important. Then recall from the previous, when we used when we had A vector dotted with B vector, we got the formula as absolute value of A times absolute value of B times cosine of the angle between them. So this time we will use the same idea here, the parallel idea, analogous idea. We will say we'll take the magnitude of vector A, multiply it to the magnitude of vector B, but this time we're going to take the sine of the angle or theta between these two vectors. Now as we can see, by definition, the magnitude of A and magnitude of B is a scalar quantity. Sine of theta is also a scalar quantity, but I already mentioned that the cross product of two vectors gives us a vector. Now here we are getting that we have the product of three scalar numbers. That's definitely going to give us a scalar number. By no means it's going to be a vector quantity. So what we'll have to do, we'll have to take this quantity, the magnitude of A, magnitude of B times sine theta, and multiply it with a special type of a vector which is referred to as the unit vector. That is why unit vector becomes very important. So here we're multiplying it with a unit vector, and this unit vector n cap has the condition that it is going to be perpendicular to A vector and also perpendicular to the vector B. And here I'm using a unit vector because the magnitude must remain unchanged. The magnitude of this particular quantity, when we multiply these three quantities, whatever magnitude we get, it should be same as the magnitude of A vector cross B vector. So in order to not alter its magnitude, I'm multiplying it with a unit vector, but this is going to give us a new direction. Its direction is neither along A vector nor B vector, but it's going to be along the direction perpendicular to A and B. That means on a plane, we must have A and B, and then perpendicular to that plane, whatever direction we get, that is going to be the direction of n cap. So a couple of results that we can immediately obtain from this formula. We can say that A vector cross B vector is not commutative, meaning A vector cross with B vector is not going to be equals to B vector crossed with A vector. That we have already established. A cross B is not going to be equals to B cross A. Then is the cross product or the vector cross product associative, meaning is A vector crossed with B vector, then we cross with C vector, is it equals to A vector crossed with B cross C? Is it going to be true? The answer is no. The vector cross product is also not associative in nature. Associative in nature. So let's try to understand it visually. Or what we'll do, we're going to consider a plane. So here we have a plane. This particular plane contains, let's say, three vectors: vector A, vector B, and vector C. Let's say all of them are having the same terminal point, a same initial point. So let's consider this to be A, this to be B, and we have vector C. So what we can do, we'll take A cross B first. So we're going from A to vector B. We're taking the cross product. That is going to give us a third vector, which is going to be perpendicular to A and V. So let's call it vector D. Now what we have to do, we have to find out D vector crossed with C vector. So we have a vector D which is going upwards, and then we have a vector C lying on the original plane. So we're taking D vector and crossing it with C vector. Now this is going to give us a vector which is going to be perpendicular to both D vector and C vector. So it is going to be somewhere in this direction. So let's call it the vector E for the time being. Now what we'll do, we will take B vector and cross it with C vector. So crossing B vector with C vector. So let's say this is the angle theta 2. So initially it had theta 1 between A vector and B vector. Theta 2 is the angle between B vector and C vector. We're taking the cross product from B to C. That is also going to give us a vector which is going to be perpendicular to B and C. Okay, fine. It is going to be parallel to D vector. Let's call it the vector F. Now what we have to do, we'll have to take A vector and then we are going to cross it with F vector. So let's say we have vector A, and now we are crossing it with F vector. Now, if we use our right hand thumb rule, now the vector is going to be, the resultant vector is going to be perpendicular to both E and F vector, but it's going to be pointing in this particular direction. Let's call it the vector G vector. As we can see here, clearly E vector, that's not equals to the vector G. They don't have the same direction. So since they don't have the same direction, we cannot say that the vector product is associative in nature. So by no means A cross B and then crossing it with C is the same as A cross when A crossing with B cross C. So I hope you have gotten an idea of what vectors are. So in today's lecture, let's quickly go through whatever we have learned in today's section. We started out by defining the difference between scalar and vector. Scalar contains only magnitude, whereas vector contains both magnitude and direction. Then we talked about how to represent the vector. So in textbook, it is usually written in a bold case letters, and for our purpose, we're going to represent it by writing the letter, and on top of it, we're going to use an arrow. So we talked about the equality of vectors. Two vectors are equal if they have the same magnitude and the same direction. Then we discussed how to add vectors. Then we also talked about multiplication of a vector with a scalar. And then we talked about how to find the difference of two vectors, that means subtraction of vectors. We got introduced to the concept of a unit vector, an extremely important concept. Take a scalar number, multiply it with some vector whose magnitude is always 1 but has got a direction, converts that scalar number to a vector quantity. So as using that, we defined a unit vector. Unit vector is defined as take a vector divided by its own magnitude. That gives us the direction of that vector, and that direction is nothing but the unit vector. Then we talked about multiplication of two vectors. We have two types of multiplication possible. One is the dot product, which is also referred to as the scalar product because the result is always a scalar quantity. Dot product has to do with projection of a vector or projection of a vector on each other. And then we have the other type of product, which is the cross product, which is also referred to as the vector product. That's because the result is always a vector quantity, and the result is such that this vector, the resultant vector, is going to be always perpendicular to the plane. It's very important. It's perpendicular to the plane that contains A as well as B. Right. So we end the lecture here today, and from the next class, we'll be picking up on more ideas on vectors. Like if we extend, we'll be extending the product to more than two vectors. So we'll be talking about scalar triple products. So there are also different types of triple products possible. One is a scalar triple product, and then we have a triple cross product. Some kind of products are possible, some kind of products are not possible. For instance, let's say we take three vectors, vector A, vector B, and vector C. Now if I say I do A vector dotted with B vector and then dotted with C vector, is this a vector? No, this is a complete wrong way of writing a vector. So think about it, why this is not true. Similarly, we can think about a vector A and then multiplying it with a number, a scalar number. And is this a correct way of writing a vector? No, this is incorrect. So we'll also talk about all the incorrect ways of writing a vector, which we'll pick up in the next class.